Hello, and welcome to today's video. After going over all the performance metrics in the previous video, I thought it would be nice to do an example video going over all those metrics given a very small example data set. And so that's what we will be doing here. I will give an example data set. I'll calculate the true positive, false negative, and true negative values for all of the data set. Then I'll calculate accuracy, precision, recall, F1 score, and then all the cutoffs and show the ROC for that data set. So with that, let me get started and explain what the data set will be. So for this data set, we are going to be looking at student grades. So the question will be, or the task would be for this machine learning problem, that you have a list of student grades. They're in a percentage scale, so between 0.0 or 0%. All the way up to 1.0 or 100%. And as maybe somebody that works in a school system, you want to try and predict whether a student would pass or fail a course given their percentage grade, and maybe some other, maybe a starting grade and some other data that we'll not go into. We'll be only looking at the labels here. So with this might be helpful in case maybe it predicts that a student would fail a course, in which case you might be able to talk to the student and give that student more help to try and get them to pass the course. So with that, let me write down the actual data set that we'll be using. So I'm going to write down the actual scores, and then we'll pretend that the data set has been run, and it will have predicted scores as well. So let me write this down real quick. Okay, so we have these scores set up now. So this is just a random test data set that I've created. These are not actual student scores for any particular class or school or anything like that. And you'll notice that I wrote these all in the decimal form for the grades. So for example, this here would be 90%. So each of these could be multiplied by 100 to get their percentage score for whatever class this might be made for. And we'll see that we have a total or n of 10. So there are 10 data points for this data set that we have. Now, for our data set, for our problem, we're looking mostly just for a pass or fail. So what we need is some cutoff value to say whether these percentage points are showing that a student will pass a class or showing that a student would fail a class. So for this case here, let's say that we set the cutoff value, and I'll write this in a different color. Say we do a cutoff value of 0.6. So anything above or equal to 0.6 will be set up for a pass, and everything below 0.6 will be a fail. So that will be what we have these data points being set to. So now with that in mind, let me now draw up the actual labels that would be used for the actual output of the algorithm. Okay, so now we have both the actual input here, so the actual scores. So this would be the actual input and output of the algorithm. And then this on the right hand side would be what we would have for the cutoff. So with the percentage points that we have on the left, it would run through some if statement at one point or another and be converted to these pass or fail grades. So this is a data set. This is the data set that we will be using for the rest of this example. So the next step in our little example here is to calculate the set of true positive, false negative, and true negative values for our labels here. And so I'll write this in green here, and we need to think about now what, again, does the true positive, false negative, and true negative actually mean. And again, just to go over why each of these are here, the true positive is because we had an actual true label and it predicted it to be true. So always think of true and for the true positive and true negative case to mean a correct prediction. So a true positive is a correct positive prediction and a true negative is a correct negative prediction. And then for the false positive and false negative, the false meaning that it is incorrectly predicted. So a false positive is a label that is actually false but is predicted to be true. So it is a false positive, one that's incorrectly predicted positive or true. And then vice versa for the false negative, it is a label that is actually true, but it is predicted to be false. So it is an incorrect false prediction. So with that now said and done, we can now go through and think of what each of these different values mean. And remember, we want to sum up everything for our label set here after it's done going through all of the if statement and calculate these false positive, false negative values with this data set. So with this, if we count up the true positive values, we would be going through looking at all the values that are labeled actually positive and predicted actually positive. So for those we have 1, 2, 3, 4, 5, and 6. Because they were labeled positive, they're actually labeled positive and they are predicted positive. So those are a 6. And then if we go through and next look at the false positive, those are the ones that were supposed to be false, but were predicted positive. So those are 1 and 2. So we have 2 false positives. And if we go through the false negative, we now again think of these are positives, but are predicted negative or false. So we just have 1 of those here. It was actually positive, but it was predicted false. So we have 1 of those. And then finally we have the false positive. So one that was actually false, but predicted to be true. And in that case, oh, whoops. I actually have false positive here written twice. So this one is actually true negative. Yep. So this is true negative we're looking for. One that was predicted, it was actually false and it's predicted false as well. So it was a correct prediction. And we just have 1 of those. So we have 1. And now if we sum up all these values here, it should equal 10. So we have 6 plus 2 plus 1 plus 1 is 10. So we know our math adds up at least. And so this would be all the different sums up for each of the true positive, false negative, and true negative values for our test data set that we have here for whatever algorithm model that we have trained. So from here, we can move on now and say, okay, what is the accuracy, precision, recall, and F1 score for our data set given these values, these true positive, false positive values, and so on. So now I've just moved us over a little bit so that way we have a little bit more room to work. And I'm going to first go over accuracy. If you remember that accuracy equals the true positive plus the true negative over the true positive plus false positive plus true negative plus false negative values. So if we look at our values that we have on the left hand side of the screen, we can see that we would have 6 plus 2 over 6 plus 2 plus 1 plus 1 is equal to 8 over 10, which is 80%. So we would have 80% for accuracy. Next on the list will be precision. So if we remember from previous video, we have precision being equal to true positive over true positive plus false positive. And so looking at that from the values on our left, we have this being 6 over 6 plus 2. So we have 6 out of 8, which is equal to 0.75. Next up is recall. So if we remember back to the previous video for recall, it is true positive over true positive plus false negative. And that is equal to 6 over 6 plus 1, which is 6 over 7, which is this 0.857143. A little bit long, but basically 0.86 we can think of. And now finally, we can move on to the F1 score. So the F1 score is, if we remember, it is 2 times precision times recall over precision plus recall. So if we look at this, it'd be 2 times 0.75 times 0.86, I'll just round up, over 0.75 plus 0.86. And luckily enough, this actually equals 0.8. So that is then the F1 score. And with all these values, we now know the accuracy and the F1 score, which were the two of the three main metrics that we had talked about in the previous video. So you can, again, there are some cases where you might only be interested in precision or recall, in which case you can just use one of those two, or both even, in a separate manner to measure the performance of your machine learning model. But in most cases, you'll use the F1 score. So now that we have all these metrics, the next one is to look at the ROC, or receiving operating characteristic. And so to do that, I'm going to give myself a little bit more room to work. And I will start out by asking, what cutoff values do you think we should use? And nobody's going to be able to respond, so I'm just going to answer. The cutoff values that, at least in my case, that I'm going to use are 0.5, 0.6, 0.7, 0.8, 0.9, and 1.0. And so, just to kind of give a brief overview of what I mentioned in the previous video, these cutoff values are what's going to be used to generate the multiple F1 scores for each interval that we work under to generate the ROC curve that we would plot then. So these cutoff values are similar to the threshold of 0.6 that we mentioned earlier when we generated this data over here. So when we generated these actual and predicted labels through the cutoff value of 0.6, that was a sort of artificial cutoff value that we implemented to start going through the accuracy, precision, recall, and F1 score. So now we're going to be doing basically multiple F1 scores. That's where the multiple F1 score for each different threshold that we come up with comes from. So these are our different cutoff values. And to plot the curve for this, we are going to need two other values here. So the one other value is 1 minus the specificity, if I remember how to spell it, specificity, and then the sensitivity. And so this 1 minus specificity will be our x on our x-axis, and the sensitivity will be our y-axis. So now comes the chore of calculating all of these different values. So I'll run through 0.5, and then I'll just plug in everything else. So for the 1 minus the specificity, and I'll just say SPE for right now, we would be looking at 1 minus whatever those true positive, false positive values would be. And for specificity, that would be true negative over the true negative plus the false positive. So that's what we get for specificity. Now, there is the 1 minus part of that is actually something, and that is the false positive rate is what it's called. And so the false positive rate is sort of what it sounds like. It is the false positives over the false positive plus true negative. So this is what the false positive rate then comes to, and that's what will be our x values. So if we just want to try and think about, okay, what exactly are we looking for this 1 minus specificity for our x-axis? We need to think about, okay, the false positive here and here are counting labels that were incorrectly predicted positive. And then this true negative are looking at all the labels that were correctly predicted negative or false. So this is looking at all of the actual negative or false labels and how their predictions came to be. So adding this bottom portion up here is looking at all the false actual labels, and the top portion here is looking at all the incorrectly predicted false labels. So it's more of a ratio of all of the incorrectly predicted false actual labels to all of the false actual labels. So that's what this 1 minus specificity or the false positive rate is. And so if we want to think about this for 0.5, we need to go back to our threshold values up here. So I will bring this up. And so for this, we're looking at our cutoff value. So we're actually going to be regenerating these into these new labels. So we're going to be generating those new pass-fail labels given a new cutoff value of 0.5. And so to do that, I will bring down this a little bit. And I'm probably going to run out of room, but I'll see what I can do here. So there will be 9 positive labels, or there will be 9 passing grades, so to speak, and then 1 failing grade with our cutoff value of 0.5 or 50%. And then going back up and looking at these passing grades here, we have or the predicted grades, we should have all of these being passing because we have none under 0.5. All right, so we now have all of our labels now, our pass-fail labels, with our new cutoff value of 0.5. So what's going to be the false positive rate? So the false positive rate for this, and just so we have it over on this left-hand side, I'll rewrite it, is false positive over false positive plus true negative. And so the false positives, again, are any... Nope, I actually did mess up. There's one thing that I messed up here. And this is why there's usually just functions available for you to use. It's because remembering these things are difficult. So the one thing that I did forget is that we do not recalculate the actual labels. So these actual labels here are supposed to be coming from what we initially did, so the 0.6. So these labels should actually be coming from here. And so we should be having the lower 3 here be failing grades. So these two should be failing. Like that. So that's one thing that I forgot to mention, is that when you do calculate these ROC cutoffs, you're going to be looking at the initial actual labels. So the actual labels before you do anything with the predicted new cutoff. So now when I go to calculate this, we would have 3 over 3 plus 0 is 1. So if we go back to our chart over here, we would be able to put a 1 for the 0.5. Now if we look at sensitivity, if we remember what sensitivity is sensitivity is equal to recall, which is equal to the true positives over the true positives plus the false negatives. And so again, going back over here, I'll just write the recall since it's the same thing, and then true positive over true positive plus false negative. And that is so the top part, the numerator is going to be all of the correctly predicted positive labels. And so we have 1, 2, 3, 4, 5, 6, 7 over all the correctly predicted positive labels and all the incorrectly predicted positive labels. So we have 7 plus 0 because we had no positive or passing grades from the actual side that were predicted to be failing. So this is also 1. So not as insightful as it could be, but that's what we need to do now for 0.6, 0.7, 0.8, 0.9, and 1.0. And luckily I have all of those figured out. So now this is all of the points that we need to generate our ROC curve. Now, if you remember, I mentioned in the previous video that we could possibly not have these thresholds in sorted order by the cutoff value. So we might not have it in, say, 0.5, starting with 0.5 up to 0.1 in sorted order, or the reverse of that, 0.1 down to 0.5 in sorted order. We might have it be 0.5, 0.7, 0.9, 0.6, 0.1, 0.8. But in this case, it just so happens that we are potentially already in sort of reversed sorted order, because the minimum is 1.0 at 0, 0. So this would actually be 0.00 on our graph. The next point is 0, 0.429, and then so on, 0.571, and so on, up to 1. So it is already in sorted order in reverse from this graph. But what I will do now is create the chart. Okay, so we have the chart here, and if you remember right, that our x-axis is our false positive rate, and our y-axis here is the sensitivity, recall, or true positive rate. So these are what our y and x-axis are. And so now we can start plotting our points, and I will do that in red. Okay, so this here, so the red part is the ROC curve. So this is what our ROC curve looks like. Not much of a curve, and well, we would prefer it to be. But if you remember, a perfect ROC curve would look like this. So it would be that would be a perfect ROC curve. So it's sort of there, but just not all the way. This is more so meaning if we look at our actual data here, we are having not very many false positives, which is good because for 1.0, 0.9, 0.8, we have 0 false positives, which correlate with our mostly straight up y, going up y-axis there for the first part. So that's at least pretty good. But the one thing to remember is that we always have two curves or point lines on this ROC curve plot. And so our third one here is chance. And so what you want to remember about chance is that it just get a few points here. If you can imagine that being a straight line, the chance plot or chance line here is just showing what a random occurrence would be. So you could think of it as if you've taken statistics where you have, say, a t-test where you might be 95% positive that something is, in that case, two means are the same. You could think of it similar here where if you would have an ROC curve that follows very closely to chance, then it's either random or nothing really to show. So you want it to be more so along the y-axis, going up to the top and then straight up the top. And you would not want it to follow this chance line here, which our little ROC curve that we have here in red is not following that very much, which is a good thing. It's mostly, as I mentioned, going up the y-axis at first and then trailing up to the side. So this is nice for visuals. It gives you a nice view of how the algorithm or the model is performing given our data that we originally saw. But what about the area under our ROC curve? If you remember, I had mentioned before that the area under the ROC curve, want to do that in red, is this. So this would be the area under our ROC curve. So what would this area under the ROC curve be? So area under the ROC. And if you remember, I'd mentioned that usually when you see an ROC plot, you would have the legend have the area under the ROC score here next to your curve. So why don't we try and calculate this? Now to do this, you have to involve a little bit of calculus. You're going to need to find either, since we have the points, you can try and calculate the area under this using the points that we have, or you can try and find a function to similarly match our ROC curve here, and then integrate that function, find the first, so 0.0 and and then 1.1, and subtract those, and you get your area. In fact, I've already calculated separately the function. I've integrated it, and so I'll just say what our integral here, so our f prime, or I'll just say f of x, even better, f of 1 minus f of 0, because we take our ending point minus our initial point, and that is 0.73 minus 0.0, which is 0.73. So this is our area under this curve. And something to note, that the line that was generated from this function does not match completely this area, so it's actually a little bit higher than this. I do have a little bit of error since I didn't go with the actual points. If you'd go with the actual points, you would have more accuracy in this area number, but for me, I can just show the line real quick. The line roughly matches this. So that yellow line there is the function y, and then this f of x here is the integral of y. So as you can see, there is quite a bit missing here, so we are probably up towards 0.8, maybe a little bit more, but for right now we could just say that we have 0.73. And so with that all said and done, we've now gone through an actual little data set with 10 data points. We've calculated all of the true positive and false positive values for those data points. We've gone through and done accuracy, precision, and recall and F1 score for that. And we've then also gone through and calculated the ROC curve and the area under the ROC curve for this data set. Now, with this example, hopefully you can understand the previous video a little bit more. If you need to, feel free to go back and watch that video again, and hopefully this helps you understand what these measurements are. In this case, there's not much difference between them. They're all about 80%, so it doesn't give, this is not a good representation of how bad things could be. This is kind of a good case for all these scores to be this similar. So with that said, hopefully you were able to learn a little bit more in this, or at least get a better grasp of how these metrics are actually calculated, where they come from. And as I mentioned in the previous video, the next actual video, this was, as I mentioned, this was kind of just a bonus video to help solidify the previous one. In the next one, I will be going over cross-validation and going over what that will do for your training your models. So with that, thank you very much and have a good day.